So, welcome you all in the problem solving class of the course Applied Electromagnetics for Engineers. I am Vivek Kumar Srivastava, TA of this course. So, currently I am pursuing my Doctor of Philosophy from Antenna and Microwave Research Laboratory, Indian Institute of Technology, Roper. So, let us start. So, before going ahead, let us see that what is the motivation behind this class. So basically, from the previous feedback of this course, it has been found that the students are facing a lot of difficulties because there is not any direct interaction between the TA and the student of the course. Okay, so to resolve this issue, NPTEL team has been assigned one TA for this course who can directly be in touch with the student and try to help them for grab the knowledge and apply it to solve the question. Okay, so for that I am assigned as your TA. Okay, so basically here I will uh, help you to uh, grab all those knowledge that has been covered in the previous week. Okay, and apply it to solve the numerical problem. Okay, so I will try to uh, uh, take some of the questions in this class. Okay, and also try to give you the answer. Okay, steps that you have to follow to add to solve the problem. Okay, so basically I will take all your queries after completing a questions. Okay, so if suppose I was unable to take all your questions due to the time constraint, so no need to worry, you have to just go to the discussion forum of this course and there you can type your question. Okay, you can post your questions, so later I will give the answer to the questions. Okay, so link of this discussion forum has also provided here. So if suppose you are unable to see the discussion forum or say find the discussion forum in the course, then by using this link you can directly found the discussion forum. Okay, so let us start. So here is the first question. So the first question is that why transmission line theory is important. So anybody from audience who can address this question, that why it is so important, why not the traditional circuit theory we can use for solving the uh, uh, yeah. So anyone who can address this question from audience side, or you can type it in the chat box also, guys. Okay, so let me give the answer. So basically this is just because of the limitation of the circuit theory. Okay, so as you all know that basic circuit theory is used for analysis and synthesis of electric circuit that is composed of by using basic elements, that is resistor, capacitors and inductors. So by using traditional circuit theory we can find the response like current flowing through the circuit, voltage across any elements. Okay, so by using electric circuit we can easily find the response. However, uh, this electric circuit is applicable only for DC circuits as well as low frequency AC circuit. Okay, like frequency of 50 hertz. Okay, which is the frequency which come to your home from directly from the grid. Okay, so corresponding to this frequency, that is 50 hertz. Okay, so the corresponding wavelength is defined as lambda is equals to c by f. Okay, so c will be 3 into 10 raised to the power 8. divided by 50. So once you calculate, you will found that the corresponding wavelength will be 6000 kilometer. Okay, so even the distance from Kashmir to Kanyakumari is near about 3500 kilometer. So you can see that the wavelength is even more than that. Okay, so corresponding to this wavelength, the size of the electric circuit will be very small. Okay, so if suppose this is the sine wave corresponding to 50 hertz, f is equals to 50 hertz. So this wavelength will be around 6000 kilometer. Okay, so corresponding to this wavelength, the size of your electric circuit will be very small. It is near about like it's a point. Okay, so here you will not get any phase difference. Okay, any you will not get any phase difference between the input and the output. Okay, so here you will not see any phase difference. Whereas once the frequency of operation is increases, let us say 100 megahertz, so in that case the corresponding wavelength is defined as 3 into 10 raised to the power 8 divided by 100 megahertz, so it is 3 meter. Okay, so here you can see that the wavelength is now very small. Okay, so compared to the electric circuit, your electric circuit, let us see, let us say this is the sinusoidal wave, so corresponding to 3 meter wavelength. Okay, so here the size of circuit will be comparable to this wavelength. Okay, so that's why you will see a phase difference between the input and the output. Okay, so that's why the traditionally used circuit theory is not applicable here. So this type of problem can easily be solved by using EM theory. Okay, so by using EM theory, this type of problem can easily be solved. However, the EM theory, like the four Maxwell's equation, okay, it composed of several integral and differential operators. Okay, so while obtaining the response, it will be the user will get a lot of difficulties. Okay, so to remove all those kind of difficulties, we will use transmission line theory. Okay, so this is the reason that uh, why people are using transmission line theory, why they are not using traditional circuit theory as well as EM theory. So if anyone have any doubt, you can please ask.
This is not clear. The integral and the differential operation increases the difficulty, whereas transmission line theory overcomes this problem. I mean, what is meant by this?
Okay, so basically, see, the transmission line, see, the EM theory is composed of various differential and integral operator. Like here you can see. So here you can see it composed of various differential as well as integral operators. So for simpler equation, we can easily solve this kind of problem. Okay, but for the problem which contains function whose integral and differential operate whose integral and differential cannot be easily achieved, so there we cannot use uh, this kind of EM theory. Whereas the circuit theory is very basic, like we can easily solve any circuit that is composed of resistor, inductor as well as capacitor. Okay, so transmission line theory what basically do, let us say it is a transmission line. Okay, so we can see a small portion of this transmission line, and there we are applying the uh, basic circuit theory. Okay, so
Hmm.
here the complexity will be very reduced.
Okay.
Any other doubt? So can I move ahead?
Yes.
So here is the second question based on the question that we have seen earlier. So there we have seen that what is the significance of transmission line theory. So the second question is that which theory is best suited for analyzing an electric circuit having an overall dimension of 1 meter. Okay, so overall diameter has been given as 1 meter and the circuit is working at a frequency of 1 megahertz. Okay, so which theory is best suitable? Like the basic electric circuit theory that we are using, okay, traditional circuit theory, transmission line theory, and optical theory. Which theory is best suited? So, anyone from the audience?
Transmission line theory.
Why?
Because here the wavelength will be 3 meter,
Yeah.
as discussed in the previous slide.
Yes. Yes.
And the overall dimension of the circuit is 1 meter, which is very less than the wavelength
Mm-hmm.
of the wavelength. And hence transmission line would be applicable here.
Yes. Yes. You are right. So, like here, you can see uh, the frequency of operation is 100 megahertz. So, corresponding to this frequency, the calculated wavelength will be 3 meter. Okay. So, this so if you see that the circuit dimension is 1 meter, okay, so there is a condition, okay, so this condition is used to check whether the circuit is electrically small or it is electrically large. Okay, so if the circuit is electrically small, then the basic circuit theory can easily be applicable. But if the circuit is the circuit dimension is comparable to the wavelength, so in that case the transmission line theory is the most suited theory that we can use for analyzing such kind of circuits. Okay, so here you can see that the circuit dimension is greater than lambda by 10. Okay, so for that reason we can say that the transmission line theory is the most suitable theory for analyzing such kind of circuits. If suppose the circuit dimension is like 10 centimeter, okay, so in that case the circuit dimension will be very small than the lambda by 10. Okay, so in that case the circuit theory is the most suitable theory that we can use for analyzing such kind of circuits. And the optical theory is the one where the length of the uh, electric circuit is very large than the lambda by 10. Okay, if such kind of condition has been seen, then optical theory is the most suitable theory. Okay, so any doubt from the audience?
No, it is okay.
Others, other can also reply, please. Okay, so here is the third question. So in the yeah transmission line theory, you have seen that the voltage equation in the transmission line is defined as V naught plus e raised to the power minus j beta x. Sorry, this will be x plus V naught minus e raised to the power plus j beta x. Okay, so here this represents the forward traveling wave, whereas this represents the reverse traveling wave. Okay, so or say backward traveling wave. So why we call this term as a forward traveling wave and this term as a backward traveling wave? So can anyone answer this question?
Because uh, if we plot this as a function of time,
Mm-hmm.
then we will see that as time increases, see
Mm-hmm.
the first portion, say I'm talking of the first portion, it will power of minus j beta x. Then if we plot that as a function of time,
Yes.
then we will see that it is as the time increases, uh, the wave is traveling in the sense, I mean, say if you take a particular point in the wave and see its locus as a function of time,
Mm-hmm.
then we will see that as time increases, that particular point is also, I mean, progressing towards the positive x direction.
Yes. Yes. Exactly. Yes, you are right. So here, as said by Mr. Sunil Gupta, that once we represent this term in time domain form, okay, like here you can see that here you have, it's a phasor form. Okay, if suppose you have
Yeah.
to find out the time domain form, then you have to take the real part of, yeah, so you have to take the real part of v naught plus e raised to the power minus j beta x into e raised to the power j omega t. Okay, so you have to take the real part. So the solution of this term will be v naught plus cos of omega t minus beta x. Okay, so let us take uh, a spatial position where time will be zero as well as position will be zero. So in this case, v is defined as v naught plus, like here. Here you can see that time is also 0 as well as x will be 0. So here the maximum value of this voltage will be V naught plus. Okay. So as time progress, so in that case, to make this uh, argument to 0, okay, x should also be increased in the forward direction. Okay. So that you can trace the V induced voltage. Okay, voltage can be traced. So as the time progress, x should also be progress in the positive direction such that this argument will be zero. Okay, so that's why this term is considered as forward traveling wave. Okay, whereas, sorry, in the backward traveling wave, what happens is that once you take the time domain form of this term, you will find v naught minus cos of omega t plus beta x. Okay, so for the case t is equals to 0 and x is equals to 0, the voltage is defined as v naught minus. So as the time progress, to make the argument 0 here, the x should be increased in the negative x direction. Okay, so like here in this, yeah, so here I think you can see that as the time progress, okay, so it will go in the negative x direction. Okay, so any doubt in this question, guys? Okay, let us go to the next question. Okay, so here is the next question. A terminated transmission line of characteristic impedance Z naught is equal to 60 ohm has a reflection coefficient at the load of 0.4. and have a phase angle of 60 degree. What is the load impedance? Okay, and the second question is, what will be the reflection coefficient uh, away from the load for a distance of zero point 0.3 lambda? So how to solve this question, can anyone tell me?
We have to use the formula of the reflection coefficient.
Yes. So basically,
ZL,
yes, yes. Please go ahead.
ZL minus, yes, 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 this way only, yes.
Yes. So here is the formula for calculating the reflection coefficient. So gamma is defined as the reflection coefficient, okay, which is defined as ZL minus Z naught divided by ZL plus Z naught. Okay. So here Z naught has been given, which is 60 ohm, and reflection coefficient is also given, which is defined as 0.4 uh, e raised to the power j60. Okay, so by using this formula you can calculate the value of z, like z is given as z naught in bracket 1 plus gamma divided by 1 minus gamma. So here you have to put the value of gamma, both magnitude as well as phase. Okay, so by using this formula you can calculate the value of load impedance. Okay, so if suppose you have got the load impedance, so the next question is, what will be the reflection coefficient uh, zero point 0.3 lambda away from the load? So I think you have gone through the lectures. In that it has been given that throughout the transmission line magnitude of gamma will be constant, only the phase angle of this gamma will be changes. Okay, once you go from load to the source, okay, from load towards source, when you go on, only the phase angle will be changed. Okay, and it has been defined by this equation. Okay, so gamma in has been given as gamma L e raised to the power minus j 2 beta z. So how you will got this formula? So as you know that the voltage is defined as Vz is equals to V naught plus e raised to the power j beta z plus V naught minus e raised to the power minus j beta z. Okay, so as you know that V naught minus is defined as gamma times V naught plus, so just put this value here. So you will get V naught plus e raised to the power j, sorry, this will be minus, this will be plus, minus j beta z plus gamma times V naught plus e raised to the power j beta z. So you can take this term constant V naught plus e raised to the power minus j beta z in bracket 1 plus gamma, oh sorry, yeah, so 1 plus gamma e raised to the power j 2 beta z. So this term defines the reflection coefficient. Okay, I think I have written, yeah, this should be plus. Okay,
Please carry on with this derivation, what you are doing.
yeah, so this represents the reflection coefficient basically. Okay, so by using this formula you can calculate that what will be the reflection coefficient throughout the line. Okay, so gamma, the magnitude of gamma will remains the same. Okay, so here you can put the value of gamma, that is 0.4 phase of 60 degree into e raised to the power j 2 beta z. Okay, so beta is defined as 2 pi by lambda. Okay, so lambda you can calculate like c by f. Okay, which will be 3, sorry, 3 into
It is not
10,
required actually
sorry.
because 2 pi by lambda, it is not required. I think 2 pi by lambda and
Yeah,
z
yes,
is equal
yes,
to
yes.
0.3 lambda.
So you can, if suppose lambda has been given, okay,
Mhm.
sorry, length has been given like 2 meter, 3 meter, then you have to calculate lambda by this method. Okay, but here as the lambda L value is given as zero point 0.3 lambda, so it will cut directly and you can calculate the value of beta into L. Okay, so you have to directly put this value here. Okay, and you can find the value of gamma, okay, away from the load at this distance. So here you can see that the magnitude of reflection constant will remains the same, whereas only the phase angle will changes here. Okay, any doubt? Okay, so next question is, a short circuited uh, quarter wavelength transmission line is connected to a voltage source of 100 sine of omega t volt and carries a short circuit current of 2 ampere. Determine the characteristic impedance of the line. So how to calculate the characteristic impedance of the line by uh, in this question? Anyone from the audience? Any idea?
From this we can get, I think, Z input impedance. I think we will be able to calculate.
No, here you have to calculate the characteristic impedance, not the input impedance of the line.
No, no, no. I'm not telling that. I'm telling that the voltage, the amplitude of the voltage is given as 100 volts,
Mm-hmm.
and that short circuit current is 2 ampere. In
Yes.
that case, the input impedance 50 ohm. Input. From them, from input impedance transformation, we can get the characteristic impedance.
No, 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 no. Actually, these two terms are different. Okay. So whatever will be the input impedance will not be same as the characteristic impedance. So here I can.
No, no, no. I'm not telling that.
Mhm.
I know what is input impedance and what is characteristic impedance.
Okay.
From impedance transformation,
Mm-hmm.
as we had derived the input impedance from the impedance transformation formula.
Okay.
Similarly,
So you are
if we
saying that
can,
Z input has been known, which is near about 50 ohm from this.
yeah, yeah. From there we can calculate the characteristic of characteristic impedance, whereas the load resistance is zero.
Yes. Okay. But there you have to define the value of beta into L, na?
Yeah, sure. Yeah,
But
yeah,
you
yeah.
don't have this value. So how can you find?
No, no, no. That is the problem.
Yeah.
Yes, yes.
So uh, first of all, I am,
Water wavelength,
yes,
water wavelength is there. That means beta L is equal to pi by 2.
beta is equals to pi, beta L is equals to pi by 2. Yes. Yes, you
Yes,
can
yes,
use
yes.
that method, I think. Mm-hmm.
Okay, okay. Please tell your method,
Yeah.
which would be better. I think.
Yes, yes. So if suppose this is the transmission line, okay. So
Mhm.
at the load end, you are short circuiting, whereas at the source side, you are just applying the voltage source. Okay.
Mhm.
So Here in the transmission line, the voltage equation is defined as V of Z is equals to V naught plus e raised to the power minus j beta Z plus, yeah, sorry, gamma times V naught plus e raised to the power minus j beta Z plus j beta Z. Okay. So gamma in
Mm-hmm.
case of the short circuited line is defined as gamma is equals to ZL मतलब 0 minus Z naught upon ZL plus Z naught. So this will be minus 1. Okay, so you can put the value of gamma here. This is defined as V naught plus e raised to the power minus j beta Z minus V naught plus e raised to the power j beta Z. Okay, so you can take V naught plus common. So this will be defined as e raised to the power minus j beta Z minus e raised to the power j beta Z. Okay, so you can divide and multiply by the term 2j in both numerator as well as denominator. So the final voltage equation is defined as V of Z is equals to minus uh, 2j V naught plus sine of beta Z. Okay, similarly you can calculate the value of current which is defined here, that is, sorry, yeah, 2 I naught plus cos of beta Z. Okay, so see, the voltage source has been applied at the source side. Okay, so you can put the value of Z is equals to lambda by 4. Okay, because it is given as quarter wave length. Okay, so here you can put the value of lambda by 4 for Z. So you can see here that 2 V naught is equals to 100. Okay, this minus j term I am not including here because this will uh, this will actually contribute to the phase. Okay, this will not contribute to the magnitude, that's why I am excluding this term here. You have to just take 2 V naught plus is equals to 100. Okay, so from here you can calculate the value of V naught plus is equals to 50. Okay, so this you have defined at the source end here, whereas at the load end where Z is equals to 0, the short circuit current is defined as 2 ampere. Okay, so from here you can see that 2 I naught plus will be equal to the 2 ampere. So here you can calculate the value of I naught plus. Okay, so Z naught has been calculated as V naught plus divided by I naught plus. So from here you can calculate the value of characteristic impedance as 50 ohm.
Okay.
Any doubt?
I will try I will try that method also, and I will tell you if the answer is correct
Yes,
or not.
yes, yes, sure.
Okay, this is a good approach.
Any other doubt? Okay, so this is the next question. So here a transmission line of length 2 meter has been given. Okay, with a characteristic impedance of 300 ohm. So here 300 ohm transmission line has been given. Okay, this is used to connect the source of 60 volt working at a frequency of 100 megahertz having an internal impedance of 300 ohm uh, and load of 300 ohm. So by using this transmission line we are connecting this source to the load. Okay, so basically uh, The dielectric constant of this transmission line is selected in such a way that the signal travel at a speed of 2.5 into 10 raised to the power 8 meter per second. Okay, sorry, unit has not been given here, but you can consider it like uh, 2.5 into 10 raised to the power 8 meter per second. Okay, so you have to determine that how much average power is delivered to the load. Okay, so any idea that how to proceed in this question? Okay, so see, first of all, a transmission line with a length of 2 meter has been given. Okay, and working frequency is also given, which is 100 megahertz. So you have to first determine the value of Z input. मतलब input impedance you have to find out. Okay, so Z input is defined as Z naught in bracket ZL plus JZ naught tan over beta L divided by Z naught plus JZL tan over beta L. Okay, so here Z naught is given as 300 ohm. ZL is also given as 300 ohm. So you can directly put this value here, 300 in bracket 300 plus J 300 tan over beta L divided by 300 plus J 300 tan over beta L. So these terms will be cancelled out. So the input impedance will be 300 ohm. Okay, so here the impedance seen by the source will be 300 ohm. Okay, so input voltage is calculated as V input is equals to 300 divided by 300 plus 300 into 60. So the input impedance seen by this transmission line will be sorry, input voltage seen by this transmission line will be 30 volt. Okay, so in time domain this input voltage is defined as V in is equals to 30 cos of omega t, and I in is defined as V in divided by 300, means this input impedance. Okay, so this will be 0.1 cos of omega t. Okay, so here you can see that the load impedance is same as the characteristic impedance of this line. So reflection you can calculate as ZL minus Z naught over ZL plus Z naught. Okay, so this will be 0. So means there will be no reflection here. Reflection will not happen here. So in that case, as this is a lossless transmission line as well as there will be no reflection here. So whatever be the input voltage at this transmission line, the same will be appear at the load in. Okay, so for that reason the load voltage will be defined as 30 volt. Okay, so in only the only thing that will change is the phase angle. Okay, which will depend on the length of this transmission line. So beta L you can calculate as beta L 2 pi by lambda, which is 3 into 10 raised to the power 8 into, yeah, 10 raised to the power 8 into 2. So from here you can
It will
calculate
not
the,
be the 3 into 10 to the power 8. It should be
sorry
2.5 into 10 to the
2.5, 2.5, yeah, thanks to correct me. Okay, it will be 2.5. So from here you can calculate the value of beta L. Okay, so once the value of beta L is found, The load voltage and load current is defined as 30 cos over omega t minus beta L, and current will be defined as 0.1 cos of omega t minus beta L. Okay, so average power delivered to the load will be RMS value of this voltage as well as current, okay, which is 30 divided by root 2 into 0.1 divided by root 2, which is 1.54. So that's how you can calculate the value of load power. Any
Okay.
doubt?
Here, for calculating the RMS, we did not need to calculate beta L also. Beta L was not required
Yeah,
actually for
I know
calculating.
that beta L is not required, but I am saying here that phase difference will be observed between the input as well as output. Okay, so that's why
Okay,
I'm considering it here.
okay, okay.
Yes. So this question is related to the previous question. So in the previous question you have seen that a single load of 300 ohm is connected to the transmission line. So what happened when one more resistance of the same value, that is 300 ohm, is connected to this load? So how much power will be delivered to the load? So that you have to calculate. Okay, so how can we calculate this? So first of all you have to find the value of net impedance, which is the parallel combination of 300 and 300 ohm. Okay, so this will be a single resistor of 150 ohm. Okay, so the net load
So
impedance
it
is,
is in parallel.
yes, yes,
It is connected in parallel.
yes. In question it has been given that additional 300 ohm is connected across the load.
Okay.
Okay, so the net load impedance is defined as 150 ohm. Okay, so the calculated reflection coefficient is defined as ZL minus Z naught over ZL plus Z naught, which will be equal to 150 minus 300 divided by 150 plus 300. So this will come minus 1 by 3. Okay, so before calculating that how much power has been obtained at the load end, you have to first calculate the input impedance that we have found in earlier here. Like here we have found that the input impedance will be 300 ohm, but here as the load is now changed, so the input impedance you have to calculate again. So this will not remain same as 300 ohm, this will change now. And after calculating the value of this input impedance, I found that the input impedance will be 466 minus j 206 ohm. Okay, so this will be the input impedance now, that is seen at the source side, yeah, at the input of this transmission line. Okay, after that you can calculate the input current as 60 divided by z source plus z in. Okay, so Z source is 300 ohm, whereas Z in is defined as 466 minus J 206. Okay, so you can calculate the value of input current, which will be equal to 0.0756 angle 15. Okay, 15 degree. So this much current is obtained at the input side of the transmission line. Okay, so the input power is now calculated as half of I square into R. So the current amplitude will be this much, and the resistance that has been obtained at the input in is 466. So that's how you can calculate the value of uh, input power. Okay, so as there is no losses is present, but due to the reflection that has been present, the power delivered at the load is defined as PL is equals to 1 minus gamma square into P in. Okay, so P in you have calculated here, gamma you have already calculated here. So you can calculate the value of load power. Okay, okay, which is the combination of two 300 ohm resistors. Okay, so this much power is delivered to this load. Okay, if suppose power delivered to the individual load we have to found, then we have to divide this by 2. So this much power is delivered to individually to this load. Okay, any doubt?
Oh,
Okay, so next question is calculate the input impedance seen by a short circuited lambda by 4 and lambda by 2 transmission line. Okay, so as we know that the input impedance is defined as Z0 into ZL plus JZ0 tan beta L over Z0 plus JZL tan beta L. Okay, so here ZL will be 0 because it is given that it is a short circuited transmission line. Okay, so ZL will be 0. Okay, now beta L can be calculated as 2 pi by lambda into lambda by 4. For this length of line we can calculate the value of beta L is equals to pi by 2. Okay, so once you calculate the value of beta L and ZL is equals to 0, you have to just put this value here in this equation. So you will found that Zin calculated will be infinite. Okay, so if for a short circuited transmission line of length lambda by 4, you will observe that if suppose it is short circuited at the load in, so it will see, you will see here open circuit. Okay, whereas once you change the length to lambda by 2, means another lambda by 4 will be added here. So in that case the Zin will be defined as, okay, first of all you can calculate the value of beta L. So it will be now changed as pi. Okay, so input impedance is given as Zin is equals to Z naught. In here ZL will be 0 and beta L will be pi. Okay, so this will come 0. So once you can short circuited at the load end of the transmission line, you will see that for lambda by 2 length of this transmission line, uh, the same will be observed at the input end. Okay, so this means that if suppose you are designing a electric circuit, okay, microwave circuit, so you have to miniaturize the length of this yeah, microwave circuit. Okay, so you have to judiciously choose the length of the transmission line. Okay, so if suppose this is ultimately short circuiting at the load in, so why you are adding this additional lambda by 2 length of this transmission line? You can just remove, if suppose you are short circuiting at the load side, so the same will be observed at the input end, so no need to add this length of the transmission line. Okay, so this will be redundant. Okay, any doubt in this question?
no.
Uh, Other can also. Join. Okay. So the next question is calculate the input impedance seen by an open circuited line of lambda by 4 and lambda by 2 length of the transmission line. So the procedure will remains the same as we have seen in the earlier question. So you have to first calculate the value of beta L. Okay, so for lambda by 4 length of transmission line, beta L is defined as pi by 2. Whereas the load impedance is now infinite because it is an open circuited transmission line. Okay, so Z input is now for a lambda by 4 length of transmission line is given as 0 ohm. Okay, so means that the if suppose this is the transmission line of length lambda by 4, so if this is the open circuited terminal, so this will now short circuited at lambda by 4 distance away from the load. Okay, so similarly for lambda by 2 length of the transmission line, the calculated beta L will be pi. Okay, so you can calculate the input impedance. You will find that the input impedance will be infinite.
Exactly opposite to the previous
Yes,
case.
yes, yes. So this shows that if suppose you are designing a microwave circuit, so you can remove this redundant line so as to miniaturize the circuit. Okay, any doubt? So that's all from my side for the today's class.